Notice the second term. Huge second term. Huge second term.
Hey, it's Tommy. Fourier analysis comes out often in physics because oscillations are common in nature. Complicated functions can be represented as sines and cosines. This is a powerful tool because we can handle sines and cosines well. Here we have a string along the x-axis with height u, and we fix the string at its two ends. So at x equals 0 and x equals L, u equals 0. We give the string an initial displacement, so at t equals 0, u equals f of x, and we release it from rest, so its initial velocity equals 0. We're going to solve the wave equation for this string. Because the equation and the boundary conditions are homogeneous, we can use separation of variables, where we assume a solution of the form of a function of space and a function of time. Plugging this into the equation, we get phi h double prime equals v squared phi double prime h. And rearranging these terms, we have phi double prime over phi equals h double prime over vh. Now, this side depends on space, the other depends on time. The only way these can be true is they both equal a constant. Only negative constants will give us non-trivial solutions. For more details, refer to the write-up in the description below. Now from here, we get the two ordinary differential equations. K squared phi equals 0. And h double prime plus k squared v squared h equals 0. With the boundary conditions phi of 0 equals phi of L equals 0. And h prime of 0 equals 0. Solving these boundary value problems, we get the eigenfunctions at sine n pi over Lx. And this initial value problem, we get cosine n pi over Lvt. Putting them together, we get u equals some arbitrary constant a, sine n pi over Lx, and cosine n pi over Lvt. The superposition principle states that the sum of all solutions is another solution, so our general solution would be the sum of all these products. Now we can evaluate our solution at t equals 0, our initial condition, and all the cosines become 1. We're left with the sines, and this all equals an f of x. Now we can notice that this is the sine expansion for f of x, and we have a formula for these Fourier coefficients. 2 over L, 0 to L, f of x, sine n pi over Lx dx. This is our final solution. This is a series of standing waves. So for n equals 1, we have this, and n equals 2, we have that, and so forth, and we're adding all of them up together. But an alternate way of interpreting our solution is to write the solution with a trig identity, where we have half the amplitude times sine of the sum plus sine the difference. So what you'll see is at time equals 0, its initial condition, and sometime later, you'll see two waves with half its amplitude traveling in opposite directions. And then they'll reflect and they'll go upside down, and then they'll interfere again, and then reflect and interfere and repeat.
This demo is inspired by a lecture from MIT. Here I've plotted the first 21 terms of a triangular initial condition. These are, in every frame of time, these are sine expansions of these two triangular waves. Notice how in the middle they all add to each other, the sides they cancel each other. These are the Fourier coefficients. The even ones are 0. And that's because we need odd functions to build our function. Here we have a square wave. It's not a perfect square because we only have a finite number of terms. The Fourier expansion does not converge uniformly if we have a discontinuous function. These vertical edges need really high frequencies to build. Again, the even terms are 0. Here we have an offset triangle. Notice here they all cancel. In the middle they all cancel each other. And here they add to each other. In every frame of time, we have a sine expansion. Here they all cancel. Now, every fourth term is 0, and that's because we've plucked our string at 1/4 of its length. The piano does the same. It hammers its string at 1/7 of its length to cancel its 7th term. Here we have this offset square to the other side. Notice the 2nd term. Huge second term. Huge second term. Here they all cancel. Look at the 2nd term as it comes up. They all cancel each other. All these work together to cancel the 2nd term. Again, every 4th term is 0, and that's because our problem is symmetric from left to right.
We've applied Fourier analysis to string instruments. We could also generalize U to other quantities, like air particle displacement or air pressure, which applies to wind instruments, or a charged particle, which applies to the particle in a box problem in quantum mechanics, or electromagnetic waves hitting a boundary. One can obtain boundary conditions from Maxwell's equations and derive the Fresnel equations. All in all, I hope I have convinced you of the significance of Fourier analysis. Thanks for watching.